Hello and welcome to this video. This is one of the first among a series of videos that we are going to have, which deals with the topic of electrostatics, which is part of the class 12 syllabus actually. So first of all, what is electrostatics? If we just go by the name, we find that the electrostatics word is derived from, it's actually a combination of two words. One part, the electro, comes from the Greek word electron, meaning amber, which was one of the historically significant object used in the study of the electrification of objects. Amber is basically a resinous substance which comes from the bark of trees, for example, which has basically solidified and it has a very good texture, and normally it is one of those substances which is quite beautiful to look at actually. Anyway, so the word electro comes from the Greek word electron. On the other hand, statics means to be at rest. So if we combine these two, effectively we can say that electrostatics deals with the study of forces, the electric fields and the potentials arising from static charges. We can actually go a bit more general, and it turns out it is not only the static charges that we're looking at, but actually those charges which do not change with time. Okay, so we can have, for example, we have a sphere which is completely spotless, so there's a very uniform sphere, and if that, let's say, is white entirely, so if that rotates, for example, it's difficult to verify or difficult to kind of distinguish whether it's rotating or no. Fine. So in that sense, this particular static will mean actually that something which does not change with respect to time. So it may happen that the sphere rotates, so it's in a sense moving, but it will be still called as a static one, because what's happening is that the density is not changing with respect to time actually. Fine. So the electrostatics therefore deals with these kind of situations where we have static charges, and whatever the forces they produce or the fields, the terms which we shall look at later on, as well as the potential, we are going to assume that these are going to be because of static charges, or at least charges which do not change with respect to time. Okay. Now if we just look at a bit of history over there, historically the credit of discovery of the fact that amber rubbed with wool or silk cloth attracts light objects, it goes to Thales of Miletus, which was in Greece around 600 BC. It was known, actually after a lot of experimentation, it was found out that if we have glass rods which are rubbed with silk, they were found to repel each other. On the other hand, some amber pieces which are rubbed with wool actually, they also were found to repel each other. However, glass rod which was rubbed with silk cloth and an amber rod which was rubbed with wool, for example, so it was rubbed with wool, they were found to attract. Okay, now we shall see exactly why this situation arises later on. However, this attraction and repulsion between bodies which have been rubbed by different objects, it was attributed to a property which was referred to, or which we just call as electric charge, and this charge is going to be acquired by the bodies due to rubbing, and we say that these bodies have been electrified. Now it was found that there are two kinds of electrification, as we have just seen for the amber and the glass rod, for example, and this implies that there are two kinds of charges. and they were simply called as positive and negative by Benjamin Franklin actually, and he named them so because they are found to neutralize each other's effect, cancel each other effect actually. So he simply called them as positive and negative. Okay. It was also found that like charges, they repel. So if the charges are both positive or both negative, they will repel each other, while unlike charges attract. And the charging by this rubbing, this particular phenomena, is called as triboelectricity or triboelectric charging actually. We shall see soon enough why some objects tend to get positively charged, some objects get negative charge in a moment. Before that, we take a look at a few of the properties of the electric charge, which we shall be dealing extensively with, because every phenomena that we study will be dealing with charges actually. So the first and the foremost thing, electric charges are of two kinds, which we already seen. They are simply called as positive and negative. The reason is that they tend to cancel out each other's effect. Next, the fact is that electric charge is quantized actually. Interestingly, it turns out that nothing requires it to be. However, the charge is quantized. What it means is that whenever we take up any kind of charge, it will be always some integer multiple of a fundamental unit, a fundamental charge actually. Now, this usually will have not much effect on what we do, as it turns out this graininess of charge often will not come into picture much. In fact, we won't be able to most often see the graininess. For example, it's almost like drinking a glass of water. We know that water is made of H2O molecules, water molecules. However, while drinking it, it hardly seems to be that graininess over there. Okay, so graininess is basically lost. The graininess is not felt. That is what we have in case of charges as well. Charges are quantized. However, it's very difficult to, most often we shall be dealing with them as if they were just kind of continuous bodies. Fine. However, you must remember that the charge is quantized, and any charge we take, Q for example, will be either plus or minus. It will be, as I said, there are two kinds over there. So the charges will be always some integer multiple of a fundamental unit, which is this E, that is the charge on an electron actually, and that charge is basically, better be taken as proton in fact, because electron is negatively charged. Proton, however, is positively charged. So we have 1.6 10 power minus 19 coulomb. This coulomb is basically the SI unit of the charge. The coulomb is the SI unit. You must be knowing that coulomb, the charge is not a fundamental quantity actually, the current is. So in terms of the current, the charge we shall see later on is nothing but current into time, and the SI unit therefore is ampere into second, which is referred to as a coulomb. Fine. You should also know that recently, or in fact it's been quite a while, and we know that even the proton and the electron, they are actually made up of some more fundamental particles, which we call as quarks. They are known to have fractional charges. However, so far they have not been isolated, as a result of which quantization still is a basic unit of E itself. Okay. The next property is the fact that charge is conserved. Whatever was at the beginning still is now. Now there are two aspects of it. Charge of the entire universe always remains constant. This is in a global sense, okay, global charge conservation. Now, global charge conservation will allow, for example, for a proton to disappear at this place right now and appear somewhere at New Delhi or New York, for example. Now, this obviously will not change the total, but this can't happen. If the proton has gone from one place to the other place, it should have gone by means of a following continuous path. So this particular idea is referred to as the local charge conservation. Basically, in a region of space, the amount of charge which is entering it, so whatever we have a region of space, whatever charge enters this region and whatever goes out in a certain duration of time interval should be the same actually, fine. Assuming that in this region of space there is no build-up of charge or there is no charge leaking from there, whatever comes in must go out. This is referred to as the mathematical form for this particular fact is known as the equation of continuity, which we shall be studying in current electricity actually. The next property is the fact that charge is relativistically invariant. Now what it means is that the charge does not depend on whether it's moving or at rest. So whether the charge is moving or at rest, it will be the same. So if somebody measures the charge of a body which has say 1 coulomb of charge, and if some other person who is moving, for example, measures, it will be still the same measurement will done, both will observe that the charge is nothing but 1 coulomb. Okay, that is the meaning that charge is relativistically invariant. We should note that it turns out the mass is actually not relativistically invariant, which means that the mass will actually depend on the speed. In fact, you might be familiar with the famous formula of Einstein, which states that mass of a body is actually equal to its rest mass m naught rest mass divided by √1 minus v by c whole square, where v is the speed with which the body is moving, while c is the speed of light in free space. Okay, so mass is therefore not relativistically invariant, but the charge is. Okay, and finally we should notice that the electrical charge is additive in nature. What it means is that if there are, if I have a body which was earlier charged, we have given it say 5 coulomb of charges, and then I put on it -3 coulomb charges, so then the total will actually become the sum of these two, which is to say 2 coulomb. So in that sense, charge is going to be added up. It's an algebraically additive quantity. We add them up by using the sign as well. Okay. Apart from there, we should also notice that there are certain substances which do conduct electricity actually. We know about them, like the wirings in homes, for example, wires, copper wire effectively. They do conduct electricity well. They are referred to as conductors. As far as we are concerned, we shall think of conductors as substances which have got ideally infinitely large amount of movable or free charges. Now when I say movable free charges, we should understand that we know obviously we know this, the fact that everything is made of atoms over there, and atoms are made of charges. They are basically carrying positive on the protons and negative on the electrons, so they are made of these charges, fine. Now what happens in the case of metal conductors in general will have free movable charges actually. Metals, for example, like copper, every copper atom will basically leave or give 1 electron, and that electron can become free and move in the lattice without much of resistance actually, fine. And that is what we say when I just talk about a movable or free charge over there. But this is not going to happen, for example, in case of like plastic or wood, because these substances, the electrons are tightly bonded to the atoms. They are not free actually, and therefore they do not have such kind of liberty or free electrons over there, fine. The electrons are bounded very tightly to the nucleus, and they can't move, in fact, fine. So conductors are substances that contain large amount of movable or free charges. We shall see that later on this property becomes very, very useful. In fact, many properties of conductors follow from this. Obviously, if I consider an electrolyte is also going to be electrolytes. They will also be conductors because they also have free charges, though they are of both kind, in fact positive, negative both, but still they are conductors over there. Fine. We can therefore say that charges can move very easily through conductors. On the other hand, if I look at insulators, there are substances that do not have free charges, as I said already, within them, like for example wood or plastic, and therefore charges cannot move through these insulators because they don't have free charges over there. Fine. We should notice that conductors excuse me, conductors, they can be charged by two methods. One of them is called conduction and the other one called induction. What's the difference between them? Well, the idea is that in case of conduction, we can charge a conductor, a metal ball for example, by touching it with already charged body. For example, there is a glass which is rubbed with silk carrying some positive charges. Excuse me. So if I touch it to this metal conductor, then some of the charges will go to the metal. So this is the charging by conduction. On the other hand, in induction, we do not directly touch the metallic sphere. Instead, for example, what I could do is we can have a metal sphere on a wooden stand. So it's an insulator over there. It's a metallic sphere which we have placed on a wooden stand. So what happens is, in this case, when I bring a charged body, like say for example, as I said, a glass rod which is rubbed with silk, but instead of touching this glass rod to the metal sphere, what I do is I ground this particular metal block. Okay, the grounding implies connecting to the earth. Earth is taken to be a conductor as well. Now what is found is that actually what will happen over here is this metal, the charged glass rod will attract some negative charges towards it, and there are a lot of free charges, they can move around easily, while the residual positive charges, they flow down to the earth. Technically what happens is from the earth the charge come to the metal sphere actually. In any case, what happens is once I bring this charged rod near the metal surface and we just ground the metal, then what happens is we have now charges coming up on the metallic ball. Fine. Now if I just remove this connection and then take away this metal rod, the charges will still remain, and therefore in that case would have charged the metal ball without actually touching it with the charged body. Okay, this is the charging by induction. Fine. And we should also notice that insulators, though they can't be charged as such, they can be still polarized. Well, insulators can definitely be charged if I put some charged object on that, or we can just put some charges from outside. That I can do always, but it can't be charged like induction. It can be charged by conduction definitely. However, the important thing is that insulators can be polarized. What it means to get polarized is the fact that if I consider, for example, let's look at an atom, like the hydrogen atom for example, as simplest possible. It consists of a positive charge and an electron gas cloud surrounding it. So there is an electron cloud which surrounds it. It's like a cloud, very very fuzzy. There is a lot of, and this is spherically symmetric. So there is an electron gas cloud whose effective center is right at the center of the positive nucleus. Okay. Now if I just bring a charged object nearby, say I just bring again a glass rod which has been charged with, rubbed with silk, so it has got now positive charges, and I bring this near to this particular atom. So what is going to happen over here is the fact that this positive glass rod will try to repel the positive center of the atom, but it's trying to attract the electron, as a result of which the atom gets distorted. The atoms get slightly distorted, the positive center tries to go away and the negative one try to come closer, as a result of which the atom gets distorted. It's no longer spherical. The effective negative center has come a bit closer to the positive charge, as a result of which this atom is said to develop a dipole moment. We just say that it's getting polarized actually, fine. In effect, the plus and minus charges have separated slightly. Obviously, if the force between the plus and minus of the atom is not enough to overcome the attraction of the glass rod, for example, the atom will get broken. It will get polarized actually, broken into the positive and negative parts. But if it is not that strong, I mean, if the positive and negative charges are separating, it gets ionized in fact. But in this case, it's going to get polarized, fine. In this case, it develops a tiny dipole moment, and that is what we say when I say it's getting polarized, okay. Now, before going further, we just take a look at one of the devices which is very, very important, and that is the gold leaf electroscope. It's a simple device which was used very early to see whether the body is charged or no. The idea is that it consists of this metal disc at the top over here, which is connected through a conductor. A rod goes down all the way inside the box, which consists of a gold foil which is stick to the entire thing, fine. There are this is circular compass which can show the level of charging when this gold leaf kind of displaces. The entire thing is placed in a box. The idea is that if I bring something which is charged and touch it, for example, if I just, in fact, even if I do not touch it, for example, let us say that we have brought in a glass rod which is positively charged but not exactly touched, what will happen is this glass rod is going to pull the negative charges of this metal disc near itself, as a result of which the residual positive charge will go away, and that positive charge goes on to this metal rod and onto the gold foil as well. And because they are both positive, the gold foil kind of deflects, okay, and the exact amount of deflection, or the more it deflects, it will give us an idea regarding how much charge. The more deflection will imply more charge, okay. Obviously, same thing will happen if I just touch it to the metallic disc over there. In that case, the charge will be actually transferred to the disc, and everything becomes positively charged over there, okay. So that is how the gold leaf electroscope works, which is basically thought of as an electrometer, or a static electrometer actually. And finally, we just take a look at, we know that when we charge two objects, they get charged, okay. We know they are going to have equal and opposite charges. The point is, when I rub, how do I know? I mean, say which one is getting positively charged and what is getting negatively charged. For that case, we have this triboelectric series, which is an experimentally verified one. We have to verify the experiment. We can't do it theoretically over there, fine. So this, as you could see over there, I mean, the human skin, for example, or we can just say, we can rub our comb in a dry season, we can just comb our hair, and even that will found to attract bits of paper over there, fine. So in this case, we find that when I rub, for example, glass and silk is somewhere over here, lower object will get negatively charged, the upper one gets positively charged. So that we know that in fact, whatever things I rub glass with, the glass will be getting positively charged actually, fine. On the other hand, we can see that there's wool coming over here, and amber is somewhere down, somewhere over here, for example, below wood. So if I rub amber with wool, for example, we know that wool is getting positively charged, so the amber gets negatively charged, okay. So that's what we have for this particular video. We shall come back. The next video will be dealing with the most fundamental, the Coulomb's law as such. That will be the next of the videos. Thank you for your attention, and see you in the next video. Thank you.